Hi everyone, thank you for joining. My name is Asad Hello and I'm a senior thermal mechanical engineer with EPC. And I'll be presenting to you some of our work developing thermal tool for quick thermal performance estimation for GaN devices. So GaN FETs have been gaining popularity due to a demonstrated exceptional performance in high voltage and high frequency switching applications. And with even with smaller size devices and better efficiency compared to silicon MOSFETs. And going to higher power levels in some application requires a cooling solution to reliably be able to push at higher power levels. So even with a smaller die size, chip-scale GaN FETs have a lower junction to case thermal resistance and can thus benefit from backside cooling or from case side cooling. And we now have a good understanding of the capabilities and limitations of heat sinks and such cooling solutions. But a simple tool would be very helpful in determining thermal performance of these FETs or ICs with different proposed thermal solutions. So in this work, we will be presenting a thermal tool based on a reduced analytical thermal model, which can be more desirable to engineers than full-blown simulations, especially at early designs, at early stages of the design. And that's for several reasons. First, designers can get quicker estimates in order of minutes rather than hours, with acceptable accuracy and with minimal user experience. And thus, this tool can be used to assess different FET configurations and different thermal solutions and assemblies. A quick background of the tool. So the basics of the thermal modeling that's used in this tool is to represent the heat conduction paths from the FET to ambient as thermal resistances in a circuit network configuration. So the model takes in different PCB, FET, and thermal solution parameters, gives estimates of each thermal resistance contribution in the network, and solves that thermoresistive circuit for the overall thermal performance metrics, such as the overall thermal resistance to ambient and the temperature rise. And this approach is applied to heat dissipation through both the PCB and through the cooling solution or the heatsink if present. And the model is developed and compared to simulations and validated with thermal testing. So for the PCB cooling path, the standard heat dissipation from the FET is through the PCB with which it has like direct electric and thermal contact. So the heat that is generated in the FETs conducts downward into the conductor layer of the PCBs, where it eventually the heat spreads radially and dissipates into the ambient from the PCB surface. And the amount of heat that can be dissipated from the PCB to ambient depends on the PCB area, the airflow rate, and the thermal properties of the PC board. The effective thermal conductivity of the PCB layers also depend on the PCB layer count and the copper weight. And these parameters are also considered in the model. There exists some additional thermal resistance between the FET and the PCB. So vias that are placed near the FETs improve conductance in the through plane direction to the inner layers of the board, and thus reducing the resistance from FET to PCB. And that thermal resistance depends on the FET size as well and the via placement. So the junction to PCB thermal resistance is estimated by the model and is seen to closely match the results observed from simulations. For the case side cooling path or through the heatsink, we can say that adding a heatsink would improve the cooling, and especially with the advantage we have of a lower junction to case resistance for CSP GaN devices. And the model components are the heatsink, thermal performance, the heat spreader, and the thermal interface materials. So the heatsink thermal resistance to ambient can be defined from manufacturers, or it can be estimated also from reduced models for either air-cooled or water-cooled heat sinks. Also, any generalized type of heat transfer from the sink surface can also be defined as an effective heat transfer coefficient and can be added to the resistive circuit model. So the thermal interface material and gap fill improve the heat conductance from the device case to the sink surface, and this thermal conductance constricts with the device area. So smaller die areas tend to have larger junction to sink resistance, but what we can do for smaller devices that we can benefit from adding a gap filler or a liquid gel TIM, which helps conduct some of the heat from the die sides as well and from the PCB top surface and further reduce the junction to sink resistance. And the resistance for TIM pads is seen to mainly depend on the FET die area and on the thermal conductivity of the TIM material and the gap fill volume. So next we consider in this model two different topology configurations. The first one is for a single FET, and also we consider the widely used dual FET configuration or a half bridge configuration. So for dual FETs, there exists some thermal coupling between the two FETs, first through the PC board and through the heatsink solution, so either through the TIM and the heat spreader or through the base of the heatsink. And thus these two thermal resistances are combined and added to the circuit network model. Also, the case side resistances are added in parallel if a heatsink is present, and this gives us a final circuit model which can then be simplified and solved for, and this gives us the overall thermal resistance values to ambient, and from that we can calculate the operating temperature rise. So I'll present now a small demo over the user interface that we developed for this reduced thermal model. And the inputs that are given to the model are first the FET parameters. So we define the FET topology as a single FET or as a symmetric H-bridge. So for now, the model only considers symmetric H-bridge and with the same FET in both high side and low side. And below that, we can select our FET, and we can see here the dimensions of those FET and the area. Also, we can put in the estimates for the losses at each FET location and the spacing for the dual FET configuration. Below that, we can also define the number of vias for every FET if present. Next, we can define the PC board parameters, and we can define the stack up, the layer count, and the copper weight. And also we can put in the estimate for the conductor area within the PCB. And finally, we can define some ambient conditions and the PC board thickness and the airflow speed. Here we can see the case side cooling parameters, and mainly if we want to decide to add a heatsink, we can define the TIM material that's used. So here we have the conductivity and the thickness of the TIM pad, and we can decide to add gap fill to increase the conductance from the FET from the die sides, and we can also add the diameter, which translates directly to the volume of gap fill used, and we can also put in the material and the size of the heat spreader and thickness, and finally we can define the heatsink as resistance to ambient or also as an effective heat transfer coefficient. So the These parameters can be provided from manufacturers, and also we also provided a calculator, heatsink calculator for handy estimations of RSA. So based on the dimensions and on the sizes of the heatsink and the fin dimensions, we can estimate using also reduced models the thermal resistance of the heatsink. So finally, the model solves for the resistive circuit, thermoresistive circuit, and it presents the results as a report for each component of the circuit model and for both board side and case side cooling. And next, if we have a dual FET configuration, we can see here the overall results for the half bridge. And finally, we can report on the final temperature rise. So for validating the model, we performed a set of thermal tests and on different size FETs. And also we used the FETs in dual FET configuration and in controlled airflow in with and without a heatsink. And we used so we used an IR camera to measure the thermal response, and also thermocouples were used and can provide readings when the heatsink is mounted. So the FETs are activated in reverse bias to control the amount of heat dissipation. Here we can see the Kelvin connections for the different VN switch node and the ground node. And also here we can see the connections for the thermocouples. So the results without a heatsink show good agreement with the models. Slight error is seen, and it's higher for lower LFM because of the higher radiative and natural convection effects. And other sources of errors could be the oversimplification of the PCB construction and assuming a continuous conducting layer in the PCBs. The measurement results with the heatsink also show good estimation of the thermal performance at different airflow conditions, and some errors present and could be because of the assuming uniform temperatures at the thermal ground planes. So the model will be available on the EPC website to support designers with the FET selection, and more features will be added later, such as the asymmetric H-bridge and more detailed via analysis and some additional cooling configurations. So in conclusion, we presented a simple reduced model and a thermal estimation tool for GaN devices. We did the analysis for different size FETs in single and in dual configurations with different PCB constructions and cooling setups. This tool is also compared to experiments and shows good agreement with the observed measured results. And the tool is packaged in a user-friendly interface, which is quick and easy to use and can support engineers in FET selection for their specific application and also to size cooling solutions if needed. Thank you, and we'll have a few minutes to answer any questions. Thanks.